Professor Ian Schott is going to address us on biomedical engineering. Ian's enthusiasm and his terrifically novel approaches to innovation is evident in his career as a chemical engineer. Ian had the great good fortune to be born in Africa too. I think he was born in Tanganyika at the time, and he was educated in Zimbabwe for a short while and in South Africa, and he finished his training here in the United Kingdom. He worked with a large number of international companies as a chemical engineer prior to 2004, at which point he started sending out and spinning off a number of his own innovative companies. More recently, he's done a lot more pro bono work, and he has been working as an advisor for many different groups. As the president of the Institute of Chemical Engineers, he was awarded a CBE in 2004. More recently, he's established the Scottish Institute for Biotechnology and Innovation. He's also the senior advisor to the House of Lords for Science and Technology. So I'd like to welcome Ian to give us his address on biomedical engineering. Thank you very much, Ian.
So, good afternoon, ladies and gentlemen, and thank you, Colin and Sir John, for inviting me here today. I have to say, I feel very much of a wild card. I'm not a Rhodes Scholar. It's the first time I've been to this prestigious institute. I feel honored to be here today. I am a chemical engineer, and I've spent a lot of my life making stuff and running businesses. And in fact, if I come back to what Sir John said about that string of medicines, I've been involved in the manufacture of many of those over the last 3 decades. During that time, I've also spent a lot of time looking at how to use biotechnology and biology to make chemicals, many of those chemicals being active pharmaceutical ingredients, some of those being biological entities, but many of those being small molecules. So today I thought I would talk about some of my own real-world experience, and although I was worried that this may not be of great relevance to you, I have to say that a lot of Sir Bruce's speech will resonate with some of the stuff I'm going to say today. So I thank you for the entree. Industrial biotechnology is sometimes referred to as IB, and this Scottish Institute was mentioned, and so the logo of that is on this chart. This institute was set up 2 years ago and connects 14 universities in Scotland with a common purpose to try and translate technology into commercial activity and improve the economy of Scotland. And I speak to you today very much from the standpoint of Britain having a world-beating science and technology base, but failing to fully leverage that into true commercial benefit. And I'm going to end up trying to discuss some of those points and presenting them as further challenges in the way things were presented earlier. Now, Colin asked me to speak as an engineer, and originally he asked me to talk about autonomous robotic systems. I know a little bit about that, but not an awful lot. I've this year been made a visiting professor to the School of Engineering Sciences here in Oxford, with a particular focus on biomedical engineering. So as it's a biomedicine weekend, I chose the title I chose, but will certainly touch on robotics and both the opportunities and possible threats they bring. So this is going to be a real romp, and I'm probably going to evoke and provoke more questions than provide answers. But I'm going to try and look through what I consider the journey of industrial biotechnology to biomedicine, and I'm going to show some examples. I'm going to consider the impact of genome sequencing, and I think this is an explosive arena, and we have just failed to capture the power yet, and I think in some cases failed to imagine the possible outcomes that are available. And I'll just touch on some of that. Earlier, Sir Bruce talked about the need to cross disciplines, and this is a real theme of mine, and it will percolate through the whole of the talk. And the essential requirement to converge physical and life sciences together with engineering principles in order to really move forward. Now, I don't mention clinicians and physicians very much, but in this context, in my thinking, they're absolutely crucial, and I hope you'll take that for granted from this talk. As I mentioned, we'll touch on robotics and artificial intelligence and then conclude with opportunities and challenges. And I think there are some quite baffling challenges, and I believe we need to put more innovative capacity into the human processes and administrative processes that we thrive on in the UK. I've lived in many different countries, and I think we have some distinctive assets that we fail to capitalize on within this national boundary. So why would one get into the world of industrial biotechnology? And I'm sure you can read faster than I talk, and I think in the discussions earlier, a lot of these points have been made. But certainly my focus has been on the prerequisites of life in terms of food and water and healthcare, both saving lives and also extending lives and improving the quality of lives. But underpinning that with greener and more sustainable processes and the ability to cut cost, not just incrementally, but substantially to change the paradigms. We talked a lot at the end of the discussion period there on pricing and reimbursement, and I think there's considerable scope to look at that whole situation completely differently. When I came back to Britain, having been away for a decade in 1999, I came back to a Britain that seemed to be cynical of science and technology, that was reveling in the service industry, that was reveling in a post-industrial era. And it seemed to me that there was something fundamentally wrong with the notion that everything in the future would be manufactured in the East. We would exploit cheap labor and do other things. And I think we've come to see that. And in the last decade and a bit, I think the UK has changed gear, and a lot of government money has gone into A, this interdisciplinary collaboration, and B, facilitating it with different institutes and different measures. So I think we're in a much stronger place to genuinely improve the economy and social infrastructure. And social infrastructure, I think, was touched on many times. Now, I've heard people talk about innovation, and a lot of time is spent on the so-called valley of death and small companies and the difficulties of engagement. And I've certainly spent the last 10 years focused on this area, and I think great improvements have been made, but there's still quite a long way to go. I'm going to flick through the next three charts very fast, because in the context of industrial biotechnology, as I said earlier, I've been looking at how to use biology to make chemicals. And although many of the early progress, much of the early progress was in the pharmaceutical industry in the 80s, which I remember, and the 90s, the reason for that was a belief that the pharmaceutical industry could afford to pay huge prices for molecules and products, whereas other industries would be much more cost restrictive. A lot of my work in the last 15 years has been to ensure that as the technology develops, one can access any price point using biology to make chemicals. And one might reflect on that and reverse the circle. So increasingly we can make commodities, we can make household products, and of course we can, I've done something wrong here. And of course we can make pharmaceuticals, which has been the main subject of today. This revolution, though, in the pharmaceutical industry took quite a long time. A lot of the foundation work started in the 70s or even earlier, and this chart shows how for decades no real sales were really achieved. And then suddenly, as we come through the 90s and past the genome sequencing milestone, there's a bit of a ramp. None of that is due to the genome sequence, none of it. And we've yet to see the real benefit of the genome sequence breakthrough in 1999-2000. So 20 years ago, if we'd looked at the top 10 drugs, not one of them would have been a biologically derived molecule. In 2013, something like 6 of the top 10 were, and moving forward to 2020, we can reliably predict 9 out of 10 drugs will be biologically manufactured or derived. So this is quite a dramatic change. And we've mentioned business, or you've mentioned business a couple of times, and it has quite big significance that may not be obvious to people. But if we take one of the 2 world-leading companies headquartered in the UK, GlaxoSmithKline, and compare the track record of drugs that have been, on the one hand, a biological process, and on the other, a chemical process, once patent expiry, and the patent life does funny things to pricing, once patent expiry arrives, there's been a complete collapse of most of the major pharmaceutical companies' small molecule drugs. However, an antibiotic has managed to not only continue to grow, to survive patent expiry, but to also benefit from further innovation that will enable that drug to be one of the first generic post-patent blockbusters. So apart from the benefit in terms of formulating or first synthesizing and then formulating world-beating drugs, in some cases drugs that wouldn't be able to be synthesized without biology, there are some strong commercial reasons for really engaging in different technology. Now, I've used this very complicated chart. I apologize to those at the back who you probably can't read it, but the point of this was to emphasize that if we're going into this world of biology to manufacture, we need to combine not only individual schools and disciplines, but whole faculties, and combine the whole world of life science with physical science and bring in computation and engineering. And we, over the last 3 decades, have progressively developed the world of genomics, proteomics, metabolomics, systems biology, and we can choose how we use this cassette of technology, which is continuing to develop. I've, in the past, spent in certainly 3 decades of my career turning right at the lights and moving into the chemical tree and looking at how to either substitute or add or complement or synthesize much more cost-effectively products within the chemical environment. One can also turn left at the lights and go into the world of diagnostics, med tech, stratified or precision medicine, and use the data and the genomic information to much more precisely match real need with real solution, rather than a lot of what happens today in a non-cost-effective way. Again, I think this was touched on earlier, the so-called Moore's law, where every 2 years computing power either doubles or the cost halves. That's been going on for decades, as is shown by this graph. These are real processors. It's not theoretical. And with that rate of innovation, you get a 32-fold increase every decade, And certainly in 1980, I was incapable of forecasting how things would be in 2015. Now, with the Genome Project, which is shown on the left, as we got to 2000, which is on the left-hand side of the chart, the rate of change of cost for genome sequencing was roughly Moore's law. So that was progressing at Moore's law until, ironically, the financial crisis. So it wasn't World War II, but the financial crisis might have stimulated something. And suddenly that graph changed. Now it could be leveling out, but that gradient is now double the Moore's law gradient. At double the gradient, the rate of change per decade is 1,000-fold. And we've yet to capitalize on that 1,000-fold rate of change, or even think about what it can do. Now, physics is blessed because physics understands that the language of physics is mathematics. And over the last few decades, physics have managed to look at modeling, computational modeling, and astrophysicists can look into the universe and they can model and predict what's going to happen in the future. And using imaging and 3D technology, you can create a perfect 3D model of what the universe will look like in 20 years' time. You can store that and wait, and in 20 years' time, go to some telescopes and compare the two, and they'll be perfect, a perfect fit. Unfortunately, as I've already mentioned, as I've already described, as I've already pictured, the world of biology and medicine is much more complicated, with many more disciplines. And even to this day, I meet many biologists who don't understand that the language of biology is chemistry. I meet many medics who don't understand that the languages of what they're prosecuting are chemistry and mathematics and computational science. So it's more complicated, and we've got a long way to go. But that brings with it opportunity. So I'm now coming back to Colin. Colin wanted me to talk about robots. And there are lots of different sorts of robots. You can have avatars that are becoming increasingly more powerful, notably in computer games. Google have got into the idea of autonomous vehicles, as have many other organizations. There are, of course, drones, which is quite a somber topic today. And most of us spend at least a large part of our career on aeroplanes, where George frequently takes over, more often than we know. Now, I'm sure that some of you in the room who are surgeons are used to some robotic type devices that are allowing you to improve the techniques you employ. But I just want to spend a moment looking at the taxonomy of surgical robots. And if we go down the right-hand side to the sort of devices I've just shown, we're really looking at telemanipulators or guided surgery. We're looking at using devices that increase the power of the surgeon with guidance and precision. But they're not intelligent devices that are actually taking it to another level. On the other hand, one can look to use different types of robotics. On the left-hand side, at more the micro and macro level, within blood vessels or the body, one could use robots that are semi-autonomous or completely autonomous. But as you move into that world, you need to really start to think about this whole concept of artificial intelligence. Now, I'm lucky to do a large number of different things. I'm a fellow of the Royal Academy of Engineering, and I've been a judge on a competition called the Mac Robot, which judges companies, businesses, for innovation. And what we look for is true innovation that's been validated in the market with commercial impact and that has a positive societal benefit. And it may seem crazy that we gave the prize to Microsoft about 3 years ago for their game Kinect. And what we saw there was an enormous amount of ingenuity in machine code learning and the way that the team had managed to completely transform the architecture of an existing machine and change the roles of some of those pieces to hugely increase the power. It was inconceivable that the previously existing game could complete the algorithms of machine code learning necessary to allow individuals to throw away the controller and just use their body to drive the game. But they did it. And at that time, we were very interested in how that could be taken for greater societal benefit. And one of the things they were looking at was how to use this to help surgeons. Now, once you start moving into that world where you don't need lots of hardware and the problems of contamination of hardware in a theatre situation, a lot of doors open. And there are other developments happening in terms of 3D visual technology, where a simple headset can allow a huge amount to happen in the virtual space in an operating theatre, for example. We're very close to a lot of dramatic technological innovation that's ready for business. I think we are less close on how to conceptually take maximum benefit from that. Now, if we start to think about artificial intelligence, which is going the next level from what Kinect was doing, there are two brands of artificial intelligence. There's artificial intelligence that's been around for decades. One of the best examples might have been the computer that managed to beat Garry Kasparov at chess. Now, that was a powerful computer with brilliant people programming it, but at the end of the day, it was in a bounded situation, very clear boundary conditions. A board with 64 squares, 32 pieces, with carefully prescribed patterns of operation for each piece. So a very bounded problem. And we see that kind of methodology used for vacuum cleaners or lawnmowers or even, I would suggest, in the operating theatre with bounded tasks. But there's an organization called DeepMind and a genius called Demis Hassabis who's really got into thinking about what he calls artificial general intelligence. Now, this is still a conceptual target, and it's about the intelligence a hypothetical machine or robot could acquire to successfully perform intellectual tasks done by humans. So as soon as you start moving into this space, a whole load of other questions start to arise about the safety of autonomy. A few of them are posed here in terms of technical and ethical issues. But certainly, Demis Hassabis, it's worth looking at his career. So he was a child prodigy. He was winning chess competitions at 8 years old. He was using the prize money to buy Acorn computers, which his parents refused to buy him. He was recoding Acorn computers when he was 10 and inventing computer games. He went to Cambridge into the computer lab, already strong in physics and mathematics. And not content with that degree, then went to UCL and went into the world of neurology and did a PhD on the neural process underpinning of episodic memory, defects in which lead to amnesia. The point I'm trying to make here is that real change often comes from individuals who have a bewildering combination of competence, capability, and thought process. And Google thought this was important enough to spend £400 million buying him and his business and giving him a role in Google. In his business, he was limited by the computing power he could afford to access. So he's actually doing something quite unusual, which is being bought by a mega company, a behemoth, but being given a real job and access to unlimited assets to try and progress and develop that further. Now, I said I would talk about bioengineering. So what is bioengineering? And basically, it's about trying to combine medicine and biology with the principles of engineering. And the principles of engineering are usually about trying to measure, model, and make or do something, and to mitigate risk, constantly mitigating risk. And these are, I think, all very relevant to this discussion about cost and affordability and doability and real innovation. So here are some definitions from MIT. I think MIT and that East Coast part of the United States is a very interesting environment for innovation and collaboration. And there's as we move from simply biological engineering to biomedical engineering, we can see that the complexity of discipline is increasing substantially. Now, I'm going to finish by starting to focus on challenges and contrasting the environment in the UK with other areas. This is a quote from a particular individual, but it's a quote that many individuals have made in terms of contrasting this particular field of biomedical engineering in the USA against the UK. And one could even think about other countries, such as Switzerland or Singapore or some of the new things happening in parts of China. So I think we've got to really look at our societal model and our institutional model as we address some of the questions. So in conclusion, I think the world of biomedical engineering and autonomous robotic systems are proceeding at exponentially increasing pace. I think global interest all over the world is also broadening and deepening, and there's substantial investment, both private and public, going in around the globe. There is an increasing convergence of some key disciplines, and the big data has been mentioned a number of times, computational modeling, and today in all the universities I am working with in the field of synthetic biology, there is still a big problem between the dry scientists with the computational modeling capability and the wet scientists, and finding not only the right way to communicate, but the right way to design the right experiments that will enable, in the shortest possible time, the best possible usage and leverage of all the technology that's available. And of course, there are clear ethical and regulatory issues all over this. Now, this is a bit pedantic because, as I've mentioned before, I've lived in lots of countries and I've seen certain things proceed at bewildering pace. And I can compare them directly. In 1984, I moved to France when Margaret Thatcher and Mitterrand shook hands on the Channel Tunnel. Every month, I drove to Calais to come back to the UK, and I saw railway lines coming to the tunnel. I also saw nuclear power stations being built. I'd done a project as a student in the 70s when Britain was the world leader in nuclear technology. By the time the tunnel opened, there was a complete network of TGVs in France with an integrated power system. 23 years later, St. Pancras opened with a small section of high-speed line. We still don't have a complete high-speed line going the relatively few miles from London to the Channel Tunnel. When I was in Switzerland, I was part of a government group looking at the Swiss solution for the euro. It took 4.5 months to have a complete solution with every business in the country using the same computer system for currency exchange with the same rounding advantages for any Swiss business. I think we are still wrestling 2 decades later with how to deal with some of these issues in Britain because of our commitment to democracy and discussion. I don't want to get rid of democracy. I don't want to get rid of honest and rigorous challenge. I do want to think about how we do things faster in the way that some of you were touching on earlier. And finally, I agree that our biggest asset is the NHS, and it's bewildering how we are unable to really leverage the power of that. And every succeeding government seems to have 2 footballs to kick around. One is NHS and the other is education. And in every other country I've lived, I've never seen this complete fetish for throwing everything into the air every 5 years, but not creating any demonstrable benefit. It's a bit like being on the Titanic and constantly rearranging the deck chairs, but not changing the fundamental structure, direction, and guidance. So I leave you with those questions, and I hope I've not bored anyone to death with my wild card contribution.
Thank you. You've almost burnt a cup of tea or coffee, which we'll have available in just a couple of minutes. Before we let Ian off the stage, any questions or thoughts? I mean, I was astonished by the power of doubling Moore's Law. It has that opportunity. Amazing what you can achieve in 5 years, I think 1,000 times, let alone 10 years.
Moore's Law's, it's 10 years is 32.
Yeah, extraordinary. Any questions or thoughts around the room for Ian or for each other? Andrew.
Andrew Link again, great talk, really enjoyed it. I was, as a pediatrician who deals a lot with children with leukemia, I was reading a book recently called The Emperor of All Maladies. And there's a wonderful chapter at the beginning there back in Boston when a pathologist Farber discovered Tyrinn would help put kids into remission back in the late 40s, early 50s. And then something magical happened that the NIH was formed in the States, and on the cancer group, they brought in young infectious disease physicians who sort of disrupted the model. So rather than using one drug, let's use 2 or 3 together like we do for multi-drug resistant infections. And that made all the difference, and now leukemia is about 85% of the kids are cured. We just heard from Great Ormond Street. There's some other exciting things happening in the gene design world with T cells. But my question for you is that when you're designing a team around a problem, and you said chemistry is sort of the language of biology, how do you design consciously or not to put non-traditional players on the team who bring a completely different perspective? And how hard is that to do, and how much thought do you give to that? But it just sort of struck me. One person may, as you said, can train in different areas and sometimes bring that together in an individual. But that's why chance sometimes. But how do you sort of design for that to bring the non-traditional players into innovation?
Okay. Yesterday we sent a report to the BBSRC for a synthetic biology research centre at one of the universities. We spent 2 hours of the last supervisory or strategic advisory board, where we've got a lot of different people from around the world. discussing exactly that point, actually. And I'm not going to say we've got it right, I don't know. But we were very troubled by the need to change the culture and the thought process. And so we decided to do three things. A, to go out, use a targeted search for particular professors with particular profiles on a worldwide basis. And secondly, we decided to go and find another centre that was different but had some relevant connection and get one of their eminent scientists. So I'm personally on the second of those tasks and confident that we can at least find somebody who I think will create some change. The other one, time will tell. But in my life, I have frequently been involved in taking over companies and moving them in different directions. And generally, that's required a complete culture change. And generally, what I have done is change the leadership team 2/3 and kept 1/3, and then thought a lot about what happens next. And I'll give you one other insight, which I got this week. I was in a meeting called Whitehall Industry Group on Monday night, and on the stage was Sir Jeremy Hayward, the head of the Civil Service, and Andrew Whitty. And Langdale, the BBC political correspondent, was asking the questions. And somehow or other, the government priority of productivity came up. And Whitty said, oh, this is all very interesting. The government's gone to McKinsey and they've gone to Harvard Business School, and there are loads of books and papers and everyone's reading them. But we've just got to get real and do something. And if I look at my business with 100 sites, a couple of years ago, if I picked the site that had the worst productivity and I put a new manager in and he put a new team in or changed the team, 2 years later, it will have the best productivity. So it's all down to leadership, and very thoughtful leadership is the key. And I think that's the key in innovation. And I've talked about siloism a bit within universities. The government is horribly siloed. The government is devoid of adequate leadership in some of the campuses it tries to legislate over. And I think that's where we've really got to focus. So it was a very rambling answer to a very good question.
Got a question, I think, from Colin. And I know we've got Heinrich's question we're going to pick up after the break. We'll talk a bit more about investment. Colin.
Just a quick question, and maybe an advertisement really. Perhaps you could comment on the use of robotics in terms of this idea of an avatar. One area of health that very seldom gets tackled is mental health, and very seldom talked about in these sort of situations. But it turns out that children can be treated more effectively in many situations in which their mental health is disturbed from many different sorts of conditions by gaming.
Yes.
It turns out that gaming hits a bit of our brain more effectively than almost anything. And currently the major funding agencies in this country are trying to find gamers to invent games that are therapeutic for children. We're all medics, we don't know the first thing about games, we know they work. So if there's any game designers out there, there's certainly a lot of work for you, and please come talk to me later. But would you like to comment on that, the use of gaming and perhaps these technologies that we know affect our brains quite substantially to make things better?
Okay, well, I'm not an expert in the field, but certainly in the Royal Academy of Engineering, where I set up the Enterprise Hub, we're running loads of competitions, and gaming technology, if I call it that, is quite popular. And I think it might be worth having a conversation outside here with you, where I wear the hat of the Royal Academy of Engineering, and I think there's some opportunity there, actually.